So welcome to the live session for the week 10 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dixit from IIT Kharagpur. I am Anant Singhal, a PhD student from IIT Jodhpur, and I'll be taking some problems related to the week 10 assignment that will help you in solving the assignment problems that have been assigned to you in the week 10. So we have almost came to the ends of the course. Uh, we have almost covered all the models, so this particular week is also an extension of the drift diffusion model that we are discussing from the past 2 weeks. We did the derivations, I mean in-depth derivation for the continuity equation, and some of the special cases that we took in the last week, such as steady state, no light, and no concentration gradient, etc. So yeah, so that will help you in solving most of the numericals. And this particular week, like most of the problems are more on the theoretical side. So yeah, instead of that, we'll be covering some more topics that are not covered very what to say comprehensively in the previous week. So one of the topics that is kind of left is the optical part, that is the optical absorption. So we do have some intensity problems in the last lecture that we saw. I mean, we had some intensity problem, like if there is some inductor one and some light goes inside it and some part of it comes outside. So what is the intensity and what are the calculations? So we did a numerical directly based upon the formulation, but yeah, we did not see the derivation behind it. So let's quickly cover that, and then we can see some of the circuits or some of the numerical problems related to MOSFET, and then yeah, then we can wrap up the today's lecture. So yeah, so till here, I hope you have done all the classes at least till here, because the MOSFET or the MOSCAP was covered in these particular classes, and if you had the understanding of this, then there will be no problem understanding in anything further. So let's start maybe some of the optoelectronic parts. So maybe I'll start with the optical absorption. So optical absorption is nothing. So if I say in very simple words, so let's say we have a semiconductor. So when it is illuminated with light, what happens is the photon either gets absorbed or they may propagate through the semiconductor. So there is a chance that they may come out, or it all depend upon the energy of these photons, right? And the band gap of this particular material also, because that is the energy that is relevant to the applied energy. So if the photon energy, we know, if it is less than the band gap, then the photons are not readily absorbed. In this case, the light will be transmitted through the material and semiconductor appear to be transparent. So what I just said, that if the photon energy, so let's say photon energy is h nu, if it is less than that of band gap, then the semiconductor appears to be transparent, and the photons transmits through the material. But in opposite, if the photon energy is greater than that of band gap, so what do you think will happen? The photon will interact, let's say, with the valence electron at the surface of the semiconductor, elevate that electron into the conduction band. That is what we have seen. And this interaction, what will create? It will create a electron hole pair, right? So this electron hole pair is created, and the excess energy that may give up the electron or whole additional kinetic energy, which will be dissipated in the form of, let's say, maybe heat or something. So this is the basic principle. So the intensity of this photon flux, so let me do some of the maths. So the intensity, which I am denoting by, let's say, IV at x, in terms of energy, so this particular thing has energy per centimeter per second, that is intensity per area. So if we assume that at x is equals to 0, okay, so at x equals to 0, suppose we have IV at 0 as, let's say, IV0, which is the initial intensity, that is when the intensity before going into any semiconductor. So it will lead to IV at x is nothing but IV0 exponential of minus alpha x. So this is a basic relation that we have, and where alpha is the absorption coefficient, right? So more will be the distance, the lesser will be the intensity. I mean, more will go inside the surface like this, so it will be decreasing exponential function. So this is IV at x and this is x. So if I try to make it maybe in some manner, so this is, let's say the surface of this is x equals to 0 and this is x equals to some L. So this is L in which the light will propagate or get through or get absorbed. So yeah, this is the basic relation where alpha is the absorption coefficient. Then we have similarly the power will be given out by power per unit area, again it will be given out. So it is directly proportional to the intensity itself, so the similar relation will come out. Then there are few more things such as the generation rate of the electron hole pair. So let me cover that. So the generation rate of electron hole pair, which is in general denoted by small g. So it is not Gm, that is a transfer inductance. So it is nothing but alpha IB by h nu, and alpha IV is that again the intensity, the alpha is again the absorption coefficient. So the intensity IVX is in units of, as I said, energy per centimeter square per second, and alpha IV is the rate at which the energy is absorbed per unit volume. So this alpha is per unit volume. By making it multiplied by alpha, it is per unit. So if we assume that the absorbed photon creates an electron hole pair, then this is the generation rate. So the unit of G will be, so if you see, this is energy per unit volume per second and this is energy. So what we are left with is number of electron hole pairs. Since it will get cancelled out, it will be, the energy will get cancelled out, it will be per centimeter cube in seconds. So let's see a very, maybe some quick numerical to make you familiarize with these. So let's say we have a semiconductor silicon bar which is illuminated by a length of wavelength 1 micrometer, let's say for the case. So what we need to do is calculate the thickness of semiconductor that will absorb 90% of the incident photon energy. Sorry, not incident photon energy. And also we have some absorption coefficient that is always given to you, that is 10 square per centimeter cube, that is 100 centimeter cube. So maybe take 1 or 2 minutes and then I'll try to solve it. Let's see. So it was a pretty straightforward problem. So let me try to solve it. So what it is saying is this. Let's say this is a semiconductor bar. So we know that this is IV0. And if 90% is absorbed, what will be remaining? It will be 10% of IV0, right? So this is x equals to 0 and this is at x equals to t. So using this, we'll calculate. So lambda is given 1 micron then alpha is also given as 100. So it is nothing, ivx is just iv0 exponential of minus x, right? So if I say, let's say this is t, since I said so, let's say the thickness is t. So what will happen at x equals to t? iv of t is, sorry, is 10% of iv naught exponential of minus x, right? So this is 10% of ivx basically. So this is the thickness that we need to calculate. So what I can say that iv at t is nothing but zero point 0.1 of iv naught, right? So zero point 0.1 of iv naught is nothing but iv naught exponential of minus alpha. So it will be t now because we are calculating at t. So which will give us some exponential of alpha t, which will give us the exponential alpha t is 10. So if I try to take ln on both sides, it will be ln 10. The thickness will come out to be nothing but ln 10 by 100, which is, so ln 10 is 2.303, so it will be 0.02303 something centimeters. So this is the thickness that will be required to absorb the 90% of the incident photon energy. So it's pretty straightforward. So maybe we can see some better problem than that. So let's say now we have some gallium arsenide sample which is at temperature 300 Kelvin, and again let's assume that the photo intensity at x equals to some at x is given by this particular value, and the lambda is given as 0.75 micron. Now it is asking at this wavelength, no, it is not asking, it is telling that at this lambda the alpha is 0.9 10 raised to 4 per centimeter cube. Now the problem is the second part that we discussed, calculate g. G is the what, generation rate of the electron hole pair. So if I go back, so this is completely straightforward. So it is alpha iv by h nu. So h nu you can calculate by using the lambda value, then alpha iv. So alpha is given and iv is also given, I guess. Yeah. So everything is given. You just need to put in the formula and you can calculate g. So if I try to say, so g is nothing but alpha iv by h nu. So using this, you can find it out. You can take 2 minutes and then I'll try to solve the problem by myself. Oh yeah. So let's, I mean, this was very pretty straightforward. So alpha is 0.9 times 10 raised to 4. So all the units are in centimeter only. So IV is 0.05. Then h nu. So h nu you can calculate separately also. It is hc by lambda, which is 6.6 minus 34. Then c is 310 raised to 8. And lambda is given as 0.75 micron. So Micron means, so it is in meter per second. Since I've taken the speed in meter, so let's take this also in meter, which is minus 6. So this will be 14, this will be minus 20. So it will be 2.64 times minus 19, which I'm keeping here. And if you calculate this, this is 23. 9 5 is 45 by 2 is around 17. So it will come out to be 10 square 21. Now again per centimeter cube second. So here don't get confused. Here since the speed is in meter per second, that is why I have changed this in meter, because we want to calculate h nu, which is energy, and the only unit that is coming out of it is electron volt. Now see a last problem for this particular topic, which is a good problem. So let's say I have taken a germanium sample, dimension 1 centimeter cross 1 centimeter. It is illuminated with 50, not 50 but 20 milliwatt of and 600 nanometer laser light. So the wavelength is low, that is why laser light. I'll show it in a kind of a figure later. So this sample is surface has 100 nanometer of lossless silicon dioxide. So it has 100 nanometer of silicon dioxide. Then this silicon dioxide reflects 1/4 of incident light. So this is a very good question. I guess this is some gate problem. So from the remaining light, so this is getting reflected. Now from the remaining light, 1/3 of a power is reflected from SiO2 germanium interface. SiO2, so we have SiO2 and then we have germanium, that is what we got to know. 1/3 is absorbed in the layer. So germanium is absorbing 1/3, and then what we are left with, and 1/3 is transmitted through the other side. Let me repeat. So we have kind of a SiO2 and a germanium sample. Let me try to make a diagram. So I have this germanium, then I have this one more material which is SiO2. So now the question is saying that it is the total incident is 20 milliwatt, having a wavelength of 600 nanometer. Then the area of this cross section is 1 centimeter cross 1 centimeter. So this is 1 centimeter and this is 1 centimeter. That is what it means. So this is 100 nanometer thick. That is what I have said. So what is happening is 1/4 of the incident light is reflected back of this silicon interface. Let me change the color. Yeah, this blue thing on the top is, let's say, SiO2, and below that, let's say we have that germanium, which is white in color for now. So 1/4 of the incident light is getting reflected from this. Then the remaining, from the remaining 1/3 of the power is reflected at the interface. At the interface means at the surface, sorry, at the SiO2 germanium interface, and 1/3 is getting absorbed and 1/3 is transmitted to the other side. So this is all the details that is given. Now it says the alpha for the germanium is, okay, it is given at 600 nanometer only, is equals to 3 times 10 to the 4 alpha is per centimeter square or cube, something like that, and the band gap is 0.66 electron volt. So what we need to find the thickness of the germanium layer. So this is a very good problem. I guess it is some gate problem way back, but it was a very good problem. So, so let's try to do it one by one. So again, it is given that the total initial energy is putting capacitance. Okay, wait. So what we have is the total incident energy. As I already told, sorry, not energy but power. It is 20 milliwatt. It is saying that from the lossless layer, 1/4 is reflected back. So that means what we are remain with. So 1/4 is reflected means 5 milliwatt is reflected back. So what is remaining is, so basically I can say that the power incident at SiO2 germanium's interface. So since 5 watt has gone back, so it is remaining is 15 milliwatt. So you in this 15 milliwatt, the question says that the power absorbed by the germanium is 1/3. So 1/3 is absorbed. So germanium is absorbing 5 milliwatts. Then power, now power going to the germanium. So since this is absorbing, so power at the germanium surface. So 15, the 5 is also gone. So what we are left with 10 milliwatt. Now from that, again it is saying the 1/3 is transmitted through germanium, right? Power transmitted through germanium is 1/3 of that. So 1/3 is, let's say 10 by 3 I'm writing for now. Okay, sorry, it is not from the surface, I guess. What was the problem? Okay, one from the remaining. Okay, from the remaining only 1/3 is reflected. So 10 was left. Okay, from that only 1/3 is absorbed and 1/3 is transmitted. So it should not be 10 by 3, it should be 15. So from 15, 5 is transmitted, 5 is absorbed, and the remaining 5 is uh, 5 is what has happened to remaining 5? So absorbed, acha, 5 is reflected. Okay, okay. So 5 is reflected back. So this is how it says. So what we can say is that is at maybe at x equals to t, which is the thickness of germanium for now, the power that is transmitted out is 5 milliwatts. And we have just seen a quick relation that the power is nothing but the exponential decay. So what we have is at x, let's say at 5 milliwatt, the initial power that was 10 milliwatt exponential of minus alpha t. So at this point, at point t, power at t is 5 milliwatt and the initial was 10 milliwatt. Since 5 are already reflected back, so 10 milliwatt is only, that is what is remaining on the surface. So this is 2.
I have one question. What
Yes.
is the difference between transmitted and the observed?
Yeah.
Isn't it?
So okay, I explained it. So we
Oh,
have two different cases. So
um,
if the energy, or if the photon energy, if we are making it, wait, sorry, what is happening? Yeah, please mute whosoever it is. Okay, which you are there. So yeah, what I was saying is, if you are having some transmission of energy, so we know that if this energy is greater than that of the band gap, then only the electron hole pair will happen, because then only the electron will get out of this and goes from valence to conduction band. But if it is less than that of the energy, so it will just absorb the energy. So this is kind of a absorption and this is kind of a transmission. So that is what it means in the problem also.
okay.
Yeah. So what I was saying, yeah. So 5 milliwatt is transmitting out, and then 10 milliwatt was at the surface. So P0 is 10 milliwatt. We need to be careful because 5 is already reflected back. So we are not 5 is getting absorbed. So we are not considering that power. So that is why we have 2 as exponential of t. So it has come to the left side. So that is why it is plus x alpha t now. So T will be nothing but 2 by ln2, sorry, no, ln2 by alpha. So ln2 is, what is ln2? Alpha is also given. Alpha is 3 times 10 to the 4 ln2.
Line 2 is 0.693.
Oh, 0.69 by 3 is 0.23 only. Yeah. So it is 0.231 micrometer. So since this is -4 and it was in centimeters, so that is why it is micrometer. So this is the thickness of germanium sample out of this whole whatever has happened to this particular material. So I've taken 2-3 problems related to this optical absorption. So let me quickly repeat again what I just said. So this week also has an extension of this diffusion model, which is a hydrodynamic model, and the derivation of this is very complex, and like I cannot explain the derivation because it is very to say very assumptions, a lot of assumptions are made, and we just come up with a hydrodynamic model. So we are covering up some of the mini topics that are there, and yeah, so that is the case for this week. And in the last, oh sorry, not the last but the second last week, we have that quantum transport model that are related to the Schrodinger part that we have already discussed in some of the classes. So we'll go in depth for the quantum models in the next class. So for today we are just covering some of the mini topics that are there, and also some of the questions that are given in the assignment from this week also, just for the sake of covering some problems. Yeah. So this is some kind of optical absorption. Let me see what else we can do. Okay, so maybe I'll not go inside this. So let us do some of the MOSFET part that has not been. So did we cover the transconductance part? I guess not. I don't know. Mm, even if we have covered, so let's try that because that is quite important, and I did not think that I spent much time on it. So if you remember, for a MOSFET, we had the ID equation. So ID is ideally 0 in the case of cutoff, and this happened when VGS is less than VT. The IDS is in linear region when first the case is it conducts, and the VDS is less than that of VGS minus VT. So it is mu n C ox W by L, VGS minus VT, sorry, what happened? VDS minus VDS square by 2. Then we have IDS as mu n C ox W by L, which is 1 by 2 VGS minus VT whole square. And this is when VDS is greater than that of VGS minus VT. This is what we call saturation. This is linear, and this is subthreshold since it is below threshold. So there are few more terms that comes out of it. So the first main term is transconductance. Do you know what is transconductance, anyone?
Change in ID current for the given change in the this VGS, the input current, input voltage.
Yeah. So okay, yeah, that is correct. So we have two different things. One is output conductance and one is transconductance. So transconductance is, as he said, the change in the output drain current with respect to the applied gate voltage. Same is the, not same, but there is one more term that is output conductance, which is the change in the drain current with respect to the change in the drain voltage. So these are the two terms that I mean, in general, what we want is in industry also we want that we should have a very good high amount of GM. That is basically the derivative of IDVG, because we want more and more current, and there should be no discontinuity and this is what we want for an ideal device, because if there will be a discontinuity, what will happen? The device will get breakdown. So now, as I said, we have two different IDs. So for GM, for linear region is different, and GM for saturation region is different. So for what we need to do, we just need to differentiate it with respect to VGS to find out both of them. So let's start with for linear region. So can you calculate and let me know what is the GM quickly? So let me write the equation.
I'll do.
So mu n C of W by L, VGS minus VT times VDS minus VDS square by 2.
Human, uh, mu and Cox W by L into VD.
Yeah,
Yes, right?
yeah, yeah,
Differentiation.
yeah. So that is correct. So the GM, it is nothing but the differentiation with respect to VGS. So this term will go away since this is constant. The only term that is left or the have the VGS dependence is VGS times VDS. So the differentiation of like X is 1 only. So it will go away, and what we are left with is GM is mu and C of W by L times VDS. Same if I talk about for saturation region. So what we have in saturation region, let me write the ID equation first. It is 1 by 2 mu n Cox W by L, and we have a direct VG relation, that is VGS minus VT whole square. So the differentiation of x square we know is 2x only. So using that we can calculate the GM, and it is now related to the gate voltage. So now you see in the linear region the GM is not even related to the input voltage. It will remain constant whatever the gate voltage you put up. But for saturation region it is a function of gate voltage. So the 2 will get cancelled out by this particular 2. It will be mu and C of W by L VGS minus VT. So this is what we call as GM sat. Yes. And this is what we call as GM link.
Yeah. Understood.
Yeah. So yeah, I mean these are some of the basic methodology. Let me try to explain you using a numerical also. So let's say we have a device having a VT of 400. So by telling the VT, can you tell what is this device? It is a N MOSFET or a P MOSFET?
And
Yeah. And because we have a positive VT, for the case of P MOSFET, we require some negative voltage to make it turn on. So again, the let's say at gate voltage 900 millivolts, I'm letting you know that the drain current is 1 milliamps. So at gate voltage 1400 millivolts, we need to find the ID. So yeah, this is a very straightforward question. And wait, is it given? No. Yeah. So it is given that the MOSFET is in saturation region. That makes it easier. So maybe you can take 2 minutes, or yeah, just wait for 2 minutes and I'll try to solve it. No problem. Okay, so we know that this is in saturation. So saturation, we have just seen that the IDS is nothing but 1 by 2 mu n C ox W by L VGS minus VT.
700 K, right?
Sorry,
No, I got different. So we have to find GM and then multiply GM with VGS, then we'll get ID, right? That's how we
no,
have to do.
GM with, I don't understand. GM with VGS means
First, we'll find GM from that first equation.
which
Okay, okay.
equation?
You can do. Okay.
Okay, yeah, yeah. I mean, this was not a problem of GM. I just wanted to find out the drain current. I mean, you cannot straight away. This is a change in current with respect to voltage. So even if you want to calculate GM, you need to like forget this. So this is GM and there is no current term in this. So yeah. So what we have is it says that at VGS 900 millivolts, we have a ID of 1 milliamp. So if I try 1 milliamps of ID is okay. So let's say this mu and C of W by L and VGS minus VT whole square. So VGS is 900 and VT is 400. So it is zero point 0.5 whole square. Similarly, we need to find the ID when the VGS is sorry VGS is given, yeah, the VGS is 1.4 basically minus VT is given, yeah, the VT is also given, it is 400, so it is 1 only. So let me write 1 square. So let's say if this is 1, this is 2, if we divide both of them we can easily find the ID. So let me, yeah, so 1 milliamps by ID is zero point 0.5 square, that is 0.25 by 1, which give me ID of 1 by 0.25 milliamps, that is 4 milliamps. So did you try something different? I don't understand what you said.
No, I did very completely different.
Okay. Did
It,
you
it
get
was very simple. Okay.
yeah, yeah, okay.
I understood you.
Okay, yeah, fine. So even if you have wanted to calculate the GM, so this is the GM, but it is different at different gate voltages. So yeah, we cannot or we should not calculate GM here.
The VGS changes in saturation.
Yeah,
I mean, GM changes in saturation region.
yeah, with the gate voltage, GM, if you vary the gate voltage, GM will be different.
Yeah.
Yeah. So maybe let's see some of the problem for this week also. I mean, they are pretty straightforward. So one of the problem that has been given in this week is under steady state for a bulk semiconductor. So we have studied very thoroughly what is steady state and what does it mean. With the uniform electric field, again, uniform means electric field is uniform. It is constant around the semiconductor. So that makes the dE by dx term 0. Steady state is also making the electric field constant basically. So what is the relaxation time? I mean, we did try different cases, but yeah, this is a straight away formula. So I'm just letting you know the formula. So the relaxation time is given by Wn minus W naught over E dot J. So I'll tell you. So Wn is a modified energy density. So you'll not see numericals from this much, but the derivation that is there, it is lengthy. W naught is the equilibrium energy density. Then EJ is a joule heating, that is common. So directly I can say option A is the correct answer for this. Then we have what is the primary limitation of hydrodynamic. Yeah, so I mean, okay, let's see what they have given. It's computationally expensive. It cannot can towards constant only. Yeah. So the main disadvantage is expensive only. So as I said, I mean computationally expensive. What does it mean? It is very like it is very cumbersome to solve a lot of differentials and all the equations. So that is why it is computationally expensive. So this is the main disadvantage. Even that is why I'm not even covering the derivation. Even I don't know how to exactly do the derivation of this hydrodynamic model, but yeah, it is very complex to do. So hydrodynamic model accounts for everything. It also accounts for transient effects. It does not take even a constant carrier distribution. So even if you want some different distributions such as Gaussian or linear, you might have seen in the TCAD that if you want different distribution, you need to apply this hydrodynamic model to get the correct IDVG characteristics or IDVD characteristics, and it is applicable for any temperature. So it involves a separate thermal model in TCAD to achieve the simulation for high temperatures also. So for this, option A will be the correct answer, that it is very computationally expensive. Then it says, what effect does carrier heating have on the velocity profile?
Can we use a next nano TCAD? I mean, does it all use it?
So Next Nano is a separate software. I mean, Next Nano also do the simulation, but so I mean TCAD is there are three four TCADs basically. TCAD is nothing but technology computer aided design. So this is like a designing software.
Yeah, yeah.
So it
Mm-hmm.
is there is one Centaurus TCAD, which is in
Synopsis.
general, yeah, Synopsis. Yeah, the Synopsis one is the Centaurus TCAD, which is what we use because it is very accurate because it has all the physical models. So Next Nano is kind of a newer model and it is basically on atomic level. So if you have ever seen TCAD, what we do in TCAD, there is some material, we make a box, we make on top of it something like that. But in Next Nano, we have the atomic level deposition. I mean, we take atoms of silicon, we deposit some more atoms of silicon over that. So that is why it is very complex. I mean, in general, for
Okay.
the quantum simulations, because those are very short channel length devices, we do prefer Next Nano because in TCAD we do not have those abilities. But yeah, you can use Next Nano if you want. I mean, if you want to learn. But again, I guess this is also not commercially available, and this is also not. But at GF it is available, the TCAD.
Okay.
Yeah, so you can see that.
Thanks, thanks.
Yeah. So the next is, what effect does carrier heating have on the velocity? So if you heat, we know that there will be more scattering. What will happen if there will be more scattering? There will be higher velocity. So what is this problem saying? It narrows the velocity, it broadens the velocity, shift the velocity. Yeah. So what it is trying to say, let's say even very basic example. So if we have a silicon, if you heat it, there will be more scattering, right? So they will have a higher velocity. I mean, this is a very straightforward problem. So it shifts the velocity distribution to a higher velocity. So let's say it is, they were moving like that, some Gaussian distribution. Once you, so let's say this is at t is equals to 0. So once you apply, they will, so let's say at this particular velocity, which is maybe in some 10 to 3 centimeter per second, something like that. So since due to the application of the energy, they will start to move and they will kind of shift to a higher velocity, all of them. So this is what does it mean, the particular problem. So the answer will be C. Okay. So the next problem is, calculate the conductivity given the relaxation time. So the relaxation time we discussed in the previous lecture, which is the recombination time, or we have even discussed the numerical in the maybe third lecture of this particular course. At room temperature is given, the relaxation time is given, the density of free electrons is given, mass is given. So you need to find the conductivity. Okay. Uh, Do you remember any formula that can be related to this?
Conductivity depends on this tau and mass, tau by m. And this,
Yeah, something like that. So yeah, you're in the right
yeah.
direction. So what we studied is, we studied the derivation of mobility, in which we said that the mobility is q tau by m star. This is the effective mass. So yeah, if you, and this v sorry, this, what is this, mu, yeah, this mu is nothing but vd by mu, q, if you remember, vd equals to mu e. So vd by e is this mu. So I guess everything is given. You just need to calculate. What you need to calculate? The conductivities you need to calculate. So okay, yeah, conductivity is again. So if you remember, conductivity is nothing but NQ mu E, right? No, not E. J is equals to sigma E. So NQ mu only. J is equals to sigma E, where this sigma is NQ mu. So everything is given, I guess. We can calculate. Okay, shall I do it? Let me do it only. So tau is mu by q. So tau is given. Where is that tau? Yeah, 0.123 minus 14. M is 9.1 minus 31. Mu is we can calculate, and it is 1.6 minus 19. So it is minus 23. This is minus 8. So that will be plus 8. Yeah. So mu will be 1.6 times 1.23. That will become 7. 9.1 into 10 to the power 7. Okay. And this term is also equals to, as I said, sigma by NQ. Right? Yeah. So we can calculate conductivity from here. So what is the value of NQ? Density of free electrons is 8.5 10 to the power 28 per meter cube, it is saying. Okay. Okay. Okay, so the options are also in meter and centimeter. So let me take meter only. So sigma is NQ, N is 8.5. What is that? So 28, which is very high. Q is 1.6 times minus 19. 1.23 times per 7 by 9.1. So this will give me 9, 7, so something 16. Oh, 6 or 16. Oh, I have written 19, 19 and so this 11. Oh, yeah, I missed something. But 28, 1.23 minus 40. Oh, it was 14.
In the last term is wrong.
Yeah. So the tau was minus 14. I wrote it as minus 4. So yeah. So that will be, I guess, 19 plus 14 is 33. 33. So minus 2. Oh. So I guess this will become minus 3 instead of plus 7. Let me recheck. So if it becomes minus 3, then is it coming 16? Yeah, it is coming 6. Okay, yeah. Now it is fine, I guess. So it is 8.5, 1.6, 1.23 by 9.1 minus 6, plus 6, and it is in meter. I mean, whatever the per meter, or yeah, it is Siemens per meter. So I think A will be the answer. Let's check. So 8.5, yeah, some 8.5, 1.6, 1.9, that is 1.9. Oh, it is 2.9. Somewhere I made some calculation mistake maybe, but yeah, it should come in 10 raised per 6 Siemens per meter inverse, and there are two options, or even three. What is the difference between B and D? There's no difference. We need to check. Let me see if I have the answer to this. Mm, yeah, it says solution is answer A. So A is the answer. Maybe some calculation mistake is there, but the method is again the relaxation time is this. So it is nothing but m into mu by q. M into mu by q is time, which is given. Everything we know, and this mu is sigma by nq. So m sigma by nq, so that will be nq square tau. So sigma will be nq square tau by m.
Yeah.
Yeah, you just need
The
to put
first
all the
one
values. You are getting A?
it is A only.
Yeah, okay, fine then. So option A is the correct answer. Okay, so it says identify the correct statements. If the length of the device is more than the scattering length and the Fermi wavelength, we classify it as diffusive. So yeah, this is correct. If the phase coherence is more than that of elastic, then the classic laws is available. Okay, yeah, I remember. Yeah, I have this. So there are a few lengths that we in general define in any device. So those three lengths are: first is the phase coherence length. So it is the distance an electron travels before suffering a phase change of 2 pi. So phase, as the name suggests, if an electron suffers a phase change of 2 pi, then that particular length is phase coherence length. Similarly, we have elastic scattering length. So it is a mean free path between the elastic scattering, like the mean free path between the collisions. So that tau time was a mean free path collision time. So similarly, it is like the mean free path, the length of the in between the collision is like the elastic scattering length, and the inelastic one is basically the distance an electron travels before losing an energy kBt. So this is the phonon scattering that we studied in the drift velocity. So there is some phonon scattering due to which we have a net displacement of 0 and then leads to the drift velocity. So before losing energy equal to thermal voltage is the inelastic scattering length, and we have certain like relations that if the length is greater than that of both elastic and the phase coherence, then we have the diffusive transport, which was option A. So that is why I said it is correct. Now option B says that if the phase coherence length is more than that of elastic, so phase coherence is more than that of elastic, so it is a quantum transport. So what it says, then the classical, so this is wrong. If the device length is more than the phase coherence length, okay, if the device length is more than phase coherence, that is I phi, that is this only, and it indicates ballistic. No, ballistic, we require the device length less than that of phase coherence, so this is also wrong. So option A is the correct answer to this directly. So this is, I mean, you just need to read about what are these three things in detail, but the main thing is the explanation of these three, that these three are the lengths that we somehow use to describe that whether the transport in any device is having, is it ballistic, is it coherence. So ballistic means bullet like, so a single direction transport. In general in MOSFET we don't want to have ballistic transport because the electrons are scattering in all the directions. So we have the drift diffusion there. I mean, we have read all about it. Yeah, and then so let's see some more problems. Hmm, where is that? Okay, let's see this. Okay, so let's say we have two devices or two transistors or MOSFETs, T1 and T2, and what it is saying that T1 and T2 both are in saturation. Yeah, so both are in saturations, and the width of the second transistor is twice that of the first transistor. right? So for T1, let's say we have a current ID1 and we have a GM of GM1. Similarly for T2, we have ID2, we have a GM of GM2. So also what it says, the overdrive voltage. So you know what is overdrive voltage or VD set?
I mean, when velocity changes, right?
Yeah, so basically,
One by channel length modulation
yeah,
concept comes in.
yeah.
That
So this VD set, this is the VD set, that is what we write as VGS minus VT. So overdrive, yeah. So what you are saying is that is additional thing. So 1 plus lambda VDS. So that is the channel length modulation. But the overdrive voltage is this VGS minus VT whole square. We know we have this. So this is kind of constant because the current saturates. So that is why we also call it as VD saturation or overdrive voltage. So it says that the VD sat for the second transistor is that twice of the first transistor. So you need to find a ratio of first is ID2 by ID1 and second is GM2 by GM1. I mean, this is a pretty easy question. Uh, does it make sense, the problem, or do you have any doubt?
yeah, understood. Yeah.
Yeah, just try it out if you can. Otherwise, I'll solve in 2 3 minutes. I've got 2 by ID1 is 4. Okay, so let me try to solve it. I also don't know the answer. Okay, so let's calculate ID2 by ID1 only. So we know that the MOSFETs are in saturation, right? That was a problem with that. Yeah. So I can write ID1 as mu n C of W2. Since we have the difference, we have difference in W and we have difference in VD set. Okay. So we have VG. Okay, I'm writing just VD set. Okay. So it will be 1 only. VD set 1 whole square. 82 is mu n C of W2 by L. VD set whole square 2. So ID2 by ID1, it is nothing but, so the difference will be ID2 is below, so it will be W2 by W1 times VD set square by VD set 1 square. So we know W2 by W1 is given, I guess it is 2, and VD set 2 is by VD set 1 is 2, so that is 2 square. Is it 8? You said 4 or 8?
No, no, it's 8, 8.
Yeah, okay, fine. So ID2 by ID1 is 8. That's all the first part. On the second part, GM, we have just seen the formula. So GM1, I can write mu n C of W by L. So W2 by L, and it was nothing but VGS minus VT, right? So this is a V over drive. So let me write like that only. VD set 2 and GM2 will be, sorry, it is mu n C of W2 by, oh sorry, this will be 1. Okay, so only the square will go away, I guess. So that will be 4, I guess. So GM2 by GM1 is VD set 2 by 1, that is 2, and W2 by W1, that is 2, so it will be 4. If I'm not wrong, GM2 by GM1 is 4. Make sense? Yeah, okay. Maybe let's try to solve one more problem and then maybe we can stop for today. Okay, let's try to see if I have a very good problem. I have few. Let's do 2 problems quickly if we can. So the first one is numerical only. So we have a VG given, what is happening, of 1.8 volts. W by L is 4. Mu and Cox is 70 minus 6 ampere per volt square. Vt is given as 0.3 volts. Lambda is there, so this is a channel length modulation, that is 1 plus lambda VDS. So this is 0.09 volt inverse, and this transistor is in saturation. You need to find Gm in micro Siemens. Does the question make sense?
Yes.
Yeah. So let me also try to solve it. You might not have the calculator with you. So IDS is 1 by 2 mu n Cox W by L. We have VGS minus VT whole square, but with the channel modulation we have 1 plus lambda VDS as an additional factor. So the GM will change a bit. So what it will do is, since we have this in multiplication a constant, so it will also remain. So 1 by 2 will go away, sorry. So mu n Cox W by L, it will be VGS minus VT, and then it will be 1 plus lambda VDS. So if we can put all the values, we can get the answer. So it is 70 minus 6, then it is 4. VGS minus VT is how much? 1.5, right? 1.5. 1 plus lambda is 0.09 and VDS is, oh, you cannot give the VDS. Can you hear me?
Yeah, yeah.
Okay, so I guess I lost my connection. Yeah, yeah. So 1 plus lambda VDS. EGS. Am I right or what? What does it say? What do we need to regulate here? So come 0109 VDS. But how come we can get VDS? It is not given.
No, PG minus VT, right? PDS. Saturation.
Sorry.
But PDS is PG minus VT. Saturation. Right?
Yeah. Okay. Okay. Yeah. Yeah. So you can keep 1.5. Yes. Yes.
Yeah.
So yeah, this will be the answer, but you need to find in micro. So this will go away. So whatever except this. So this is 280. 280 times 1.5 is half of 360. No, sorry. 420. 420 times of this thing. Yeah. So this is 1.1 only something. So it will come out to be approximately 400 something microsiemens, I guess. I hope it is correct.
476.4. Oh, 476.7
Yeah. Yeah. Something like that.
microseconds.
Okay. So let's do a quick GM problem and then maybe we can go. So now the question is VGS is zero point 0.7 volts, VDS is 0.1 volts, and for this case mu and Cox is 100 microamps per volt square. The VT that is given is zero point 0.3 volts. W by L is 50. Need to find GM. The unit should be milliamps per volt square. Oh, sorry, milliamps per volt. This is very easy. So let's try out and let me know what is the answer that you are getting.
But here, channel length modulation is not given,
No, no, no. So assume lambda to be 0. Is it in linear or saturation region?
right? If VDS is given, should be
VDS is zero point 0.1. VGS minus VT is 0.7 minus 0.0, zero point 0.4. So VDS is less than that of VGS minus VT. It means it is in,
okay. Linear.
yeah. So we can get the GM directly. So GM for linear region, we know it is mu n C of W by L and only VDS. So everything is given, I guess. So 100 micro C of, okay, it is gone. So W by L is 50 and VDS is zero point 0.1. So you want in milli. So this is 100, this is 10, and this again makes it 100, 500. So 5 into 10 is for minus 4, or zero point 0.5 is for minus 3 ampere per volt, and we can say zero point 0.5 milliamps per volt, right? So zero point 0.5 is the correct answer.
Yes.
Fine.
Yeah, yeah.
Okay,
Thanks.
next. So yeah, I guess yeah, we can stop for today, and in the next lecture we'll see some of the quantum part and maybe quickly wrap up the course. So is there any doubt in this particular lecture?
No, no.
Okay, fine. Then let's meet
Okay.
next week.
Yeah, yeah.
Yeah. Bye.
Thank you, Anant. Bye.